Welcome back to the classroom. My name is Mr. Wong, and we're going to go through something slightly different today. We're going to go through some multiple choice questions from the additional sample paper. So this is going to be focusing on Module 8, which is from the universe to the atom. It includes things like quantum physics, emission spectras, also radioactivity, things like that. Okay, so let's start with question 1. So with question 1 here, it says that we have a Hertzsprung-Russell diagram shown here below. On the y-axis, we have the solar luminosity. Now, if you recall, luminosity is brightness, and then we have surface temperature. You can see that surface temperature is linked with brightness here, at least with the main sequence stars that we have. So let's have a look at the question. It says, which region would a star have the same surface temperature as a star on the main sequence star? So we have position R, Q, S, and P. Let's see what the options are. So we have A, B, C, these options here. If you actually have a look at our diagram here, S is actually the only one that's in the main sequence. So in that sense, S would be the one star with the same surface temperature as the main sequence. Or let me say that again, Q and P are way too cold, or their temperatures are way too low. And for star R, their temperature, surface temperature that is way too high for its particular main sequence. So it doesn't match. So the answer would be S, and that means we would go with D. Okay. All right, so we move to question 2. There's a total of about 10 multiple choice questions from the sample paper, so we'll go through all of them. We have the Hertzsprung-Russell diagram shown to classify different stars. You can see the S region, R, Q, P. You know for sure that the R region is the main sequence. So let's look at what the question's asking us to look at. Okay, so it says stars in region S of the diagram are much dimmer. So you can see here, and you can also see in terms of luminosity, it's quite low in comparison to the other sections. What property of the stars in region S explains their relatively low luminosity? So what explains for why things look dimmer? Okay, so one we have here, they are cooler than other stars. Now, just to point out with this kind of question here, you can see with the classification OB, A, F, G, K, M, this is the different type of classes the stars can be in. At the same time, it also can be classified into surface temperature. Okay, and we already know that O has the highest temperature, surface temperature that is, and M class has the lowest temperature. So from what we can see here, all the stars in region S, they're actually relatively high in terms of surface temperature. So that can't be the exact reason why their luminosity is much dimmer, as you can compare with I and Q. Okay, so that's probably out of the question there. We have B, they have a smaller mass than other stars. Again, in terms of the surface temperature and mass are related to each other as well. So the more massive the star, the luminosity tends to be a lot brighter as well. So B is not the correct answer. Okay. We have C, they have a smaller surface area than other stars. Okay. So if it has a smaller surface area, that could represent why it's dimmer. So we'll just leave that there for now. And then we have D, it says they are further away from Earth than other stars. Now, the way luminosity works is it measures the absolute brightness. So it's not actually measuring how bright it looks like from our perspective, but the actual brightness in space. Okay, so that wouldn't be an explanation either. So the answer in this case is actually C. It's because they have a smaller surface area than other stars. Brightness. We can work that out in terms of the intensity based on the actual intensity of the light source. So the absolute, which is actually luminosity that we're looking at here, divided by the surface area of a sphere. Remembering, with stars, we tend to interpret it as quite spherical. Now, assuming that this value here, the apparent brightness, doesn't change, it stays the same, meaning by where I'm positioned, it looks the same regardless. If the surface area is smaller, you can see how the absolute intensity or the luminosity would also have to decrease to allow us to have a constant apparent brightness. So that's kind of the explanation there. Well, what we could say is, assuming that this is a constant value, let's say call that 1, we can find that the absolute value and the surface area are directly proportional to each other. So if this goes down, that also goes down. Okay, so let's go to question 3. Okay, question 3, it says, after a DC voltage was applied to an apparatus containing hydrogen gas, the hydrogen separated into streams of oppositely charged particles. What could be concluded from this observation? A. Hydrogen gas conducts electricity. Well, that's not true. We know that hydrogen gas is a non-metal, so they're not really good at conducting electricity. Hydrogen is the simplest element. That's not true either. So it's actually C here. Hydrogen has components. Why do we say it has components? Because, so think about it this way. Hydrogen and a hydrogen atom is basically one proton in the center nucleus with one electron. Okay? If we can separate this into just the electron component and the proton component, then that registers that there is something smaller inside the hydrogen atom itself. So the oppositely charged particles that we see that gets broken down in this question here is actually the electron and proton being released. And because the hydrogen atom is actually consists of both these in one area of space, the fact that we can split them up means that hydrogen isn't the simplest element. The concept of the most simplest type of matter means that it can't be broken apart. In this case, because it can, that's why C is correct, because it shows it has components of electrons and protons. Alright, moving on to question 4. Okay, so question 4, it says, which of the following is true in relations to Millikan's oil drop experiment? So what was the aim of the experiment? Well, the aim of his experiment was to measure the charge on an electron. So C or D could be correct here. The next question is, what did he actually use in his experiment? So what type of field? Did he use electric, magnetic, or both? So he actually used only electric fields. Here's a bonus tip for you as well. He also technically used gravitational fields. So if you remember in his oil drop experiment, it was between sort of two charged plates. The oil was dropped down due to gravity, and then one plate was positive, one plate was negative, and that kind of suspended the oil drop in the center, and that's how he used that to work, or he equated the forces to work out the charge of the electron from there. Okay, and so we go to question 5. Okay, so question 5, it says, in an experiment, an electrically charged oil drop, again this looks like it's about Millikan's experiment, suspended in the air by an electric field. So confirms what we talked about in the last question. The electric field could be adjusted to balance the weight of the oil drop. If more drops were suspended and measurements taken, which of the following properties would all of the oil drops be observed to have in common? So we need to understand the part of this experiment, besides it showing the number that demonstrates what the charge on an electron was. So he didn't exactly find the correct number that we know today. It was quite close. It was about like minus 1.59 times 10 to the power of 19 coulombs. I think it was roughly around there, I think. So that was one thing. But the fact that we got a value, an exact value, represents this idea of quantization. Okay, so it shows us that charges would come in quantized numbers. So it wouldn't be mass. Mass doesn't come quantized. So the charge of each droplet would be a multiple of fundamental charge. The charge of each drop would be the same as each of the other drops. So C is actually the correct answer here. So what he actually found was he found integers or intervals of the same charge number, but in different integers. So it could be 2 times 1.59 or 3 times 1.59. But what he found was he was actually finding multiple electrons onto that oil drop rather than fluctuating numbers. It was actually a fixed interval of differences that he was witnessing there. Okay, so let's go to question 6. Okay, so moving on to question 6, and if we have a read of the question, it says the table shows the quantum numbers of the 4 lowest states of hydrogen atom together with the energies of those states. As you can see here, which quantum transition will absorb a photon of wavelength 102 nanometers? Now, the key part is transition absorb. Okay, so if it's transition absorb, we are going up the table. Okay, so it needs to either start at 1, 2, 3, whatever, but it needs to go up. So that means we can already rule out B and D. Okay, so that's the concept there. Now, I can actually solve this really quickly by elimination, but I'll also show you how to perform the calculations as well. Now, the first thing is it says which quantum transition produces this particular wavelength. This wavelength is very short. So short wavelengths relate to UV radiation. If you actually look at this transition 2 to 4, that, remember, the ground state for 2 always quantifies with visible light. So just by looking at that, I already know A is the correct answer. Okay, I don't really need to do anything additional to that. But say if I wasn't really sure, I want to cross-check it with some kind of equation. Well, you can, because you can use Rydberg's equation. So Rydberg's equation is 1 over lambda equals to the Rydberg constant, and then 1 over the final transition number and the first initial transition number. Okay, you could plug in the value for the wavelength as 1 over 102. Make sure you convert that into correct SI units. And then you have the Rydberg's equation, which is to the power of 7, I do believe. Let me just quickly check. That is correct. And then the final state would have to be 3 squared minus 1 squared there. So as a matter of fact, let's just not include the wavelength here. Let's say we want to find the wavelength, because it's probably easier to just type this into your calculator than it is to actually plug it in, substitute like so. Okay, so let's move on to question 7. Alright, question 7. As you can see, we have a radioactive decay graph here. It says a 5-gram sample of radioactive strontium-90 decayed over time. The graph shows the mass of strontium-90 remaining from the initial sample. So we started here and then we got all the way here. That's in time of years. It says, what is the approximate value of the decay constant in year for strontium-90? So let's just scroll down. These are our values here. Let's actually look at the appropriate equation for answering this. So there are two equations related to radioactivity. Okay, so we have this equation here. And this equation here. Okay, so we could use the first equation or the second one. Because we're only trying to find the decay constant, which is what lambda is, we can just use this equation here to make life simpler for us. So this is log 2. You can just put that in your calculator. T half is the time taken for the decay of one half-life. Right, so half-life is how long it takes for the initial 5 grams to decay to half of 5 is 2.5. So if I write this across, you can see it is the value of 30 here. So plug 30 years in. The value that I get in my calculator is 0.0231. So that's approximately closest to D. And that's how you do that question there. So let's move on to which question are we on to? Question 8. Okay, so it says the following equation describes the natural decay process of uranium-238. Which row of the table describes the changes in the total mass and total binding energy in the decay of uranium? Okay, so what we know is if we break the isotope apart, we will expect a decrease in the total mass because mass defect will occur in both sides. And so the next question is, if we have a decrease in total mass, does that mean greater binding energy or a lower binding energy? Okay, so for this response, the correct answer is A. We'll have a total or an increase in the total binding energy of these two constituents. So let's just go through the understanding. We always get mass defect when we have a radioactive decay. And then in terms of working out if we have increased or decreased the total binding energy, you can actually tell because uranium, I'll show you, this is the individual binding energy of the nucleus. You can see with uranium, it's relatively low. So as it decays and into helium and into thorium, you can actually see it actually increases in terms of its overall binding energy there. So that's the response for that question. Okay, so the graph plots isotopes in terms of their numbers of protons and neutrons. When isotope undergoes nuclear decay, it will move to a different location on the graph. The movement can be repeated with an arrow. Okay, so you have the number of neutrons, you have the number of protons down here, and you have the line of stability. Which arrow would correctly describe beta negative decay? So an electron decay. Okay, so let's just get an understanding. The idea of radioactive decay comes down to the mass to charge ratio. NZ ratio is usually what they say. Z is due to protons, number of protons, and then the mass number is obviously number of neutrons, number of total constituents. Now say if we have a really high charge, or we have a really high ratio number, say over here, and we have really low over here. So low over here, high over here. Okay, so if it's really high and we want to, so say the line starts off around here, we want it to come down here. We want to increase our charge number. So if we want to increase our charge number, we would go through beta decay. So which arrow would correctly describe a beta negative decay on the graph? If we get a beta negative decay, it means the Z value will increase, which means that pushes the graph down in this direction. So let's have a look. In that case, A would be the correct answer. Alright, we will move on to question 10, which is our last question of this additional sample. Okay, so we finally reached our last question. A patient is given an injection containing that amount of radioactive technetium-99m, which has a half-life of 6 hours. How much remains undecayed when a scan is taken 4 hours later? Okay, so again, we go through these two equations to work out the value. We need to firstly work out what the decay constant is, or else we won't know how much we have left. NT is obviously the quantity we want to find, or the amount that's remaining afterwards. So we'll leave that later on. We need to find the decay constant. That should be 2, not lambda. The half-life is 6 hours. Okay, so we'll leave it in terms of that being our time frame. If I put that in my calculator, let's see what value I get here. So our decay constant is 0.115, like so. Obviously, this is in SI units of kilograms, so we might need to convert this into seconds. So let's have a look. Okay, so we won't need to convert this into seconds because the time frame we're using is also in hours. So we can leave it as it is, just add an additional component. So N0 is the initial quantity that we had, and that's 0.6, 10 to the minus 18 times the exponential e, and then to the power of negative 1155, that's our decay constant that we found down below. And then we times that by time of 4 hours, we get a value of roughly 3.78, 10 to the power 18 kilograms, which means that C is the correct answer. And that concludes all the questions that was in the additional sample paper, multiple choice wise, for Module 8. If you found this video useful, give it a like, and I'll see you next time when I go through other multiple choice questions or exam questions as well. Take care.